Vehicle Structure, Chassis and Axle System. In this unit, students will first design and build a vehicle chassis for an experimental test. On the basis of this chassis, we can continue to develop the shape of the car body and improve our high-pressure air-speed car in terms of performance refinement. All optimization experiments can achieve our engineering design optimization goal through the modification and advancement of the chassis system. The car is a very complex machine. It includes many systems, such as the transmission mechanism, the frame and body, the interior, the steering, the brakes, the wheels, the suspension, the spring, and shock absorbers, as well as the power system, which can be an internal combustion engine or an electric motor. There are many parts combined in these systems, so there are about 10,000 to 20,000 parts in a regular passenger car. For the assembly of these parts, the structural design must be very strong. So that each system can work properly, it is a basic requirement of vehicle design. The sturdiness and safety of the car body's structural strength is a basic requirement for vehicle design. Vehicle design, due to its structural complexity and the severity and changeability of the driving conditions, so its structural load is very complex, which includes pulling force, compression force, longitudinal bending, shear force, bending force, torsion, and friction between parts. These forces make the structure of the car body a complex and huge project. There are two main types of body structures. One is the ladder frame type, and the other is the monocoque frame structure. Whether it is the design of a small vehicle or a motorcycle, these are the two main types of structure. Generally speaking, the monocoque frame design has the following three main advantages. 1. Larger passenger space. 2. A more comfortable ride due to shock absorption. And 3. A more comprehensive protection for passengers. Therefore, presently most cars that are sold use the monocoque frame as the main structural design method. Let's have a look at the animation of the monocoque frame of an Audi A8 to understand the design of the monocoque frame body structure. The monocoque frame body structure is composed of many steel plates or casting parts. The Audi A8 design that we see here is a very original monocoque frame structural design, which includes the aluminum alloy parts shown in red. High-strength steel plates, aluminum material used as sheet metal for the car body surface to make the body more light-weighted. These aluminum connecting joint parts are designed with many ribs to increase the structural strength while also decreasing its weight. The parts of the body structure that require strength are forged from high-strength steel, which can withstand forces such as front impact collisions. Torsion suffered by the vehicle body from bumps on the road or rollovers. When the vehicle is subjected to a side impact, the overall frame is used as a force dispersion structure, which is the strength advantage of the monocoque frame body structure. It can protect the safety of its occupants in the passenger's area to the maximum extent. These complex and diverse materials and structural designs are a complete protection mechanism for the body structure, making the vehicle structure safer and the passenger space more comfortable. This is the biggest advantage of the monocoque frame design. The car ladder frame body structure design mainly has the following two advantages. 1. Better load capacity, and 2. More flexible design space. Therefore, we can use the same chassis design and make different body structures. Next, we are also going to watch some videos regarding the ladder frame design structure and understand what kind of body structure design it is. What you see now is the ladder frame of the structure. The main structure of the ladder frame is made by the welding of different metal bars. It can bear a relatively large amount of weight, so this type of structural design is generally used in trucks, vans, or off-road vehicles. The design of the car body structure is closely related to the engineering materials used. The ability of diverse design application from the in-depth high school curriculum material is an extension of our learning content. Therefore, for the topic of vehicle structure and engineering material application, we use structural design materials with higher strength in the design of our vehicles, chassis, and axle systems. The material processing part includes the application of many types of metals and processing techniques. For body styling, we use materials that are easy to cut and shape to manufacture a prototype and has adequate strength to perform all test conditions. Non-metallic materials, such as wood or foamed plastic, are most likely to be used as material for body styling. Here is a conceptual knowledge of the application of materials in structural design. Specific strength of a material. The specific strength of a material is the strength of the material divided by its density. Specific strength is a very important concept in the design of traffic and transportation vehicles. Under this concept, we can use materials with higher strength and lighter weight to achieve higher structural strength in terms of the design of means of transportation and a better results in terms of energy efficiency. In the following table, we can see that the specific strength of some commonly used materials with high specific strength, such as composite materials, are suitable for the manufacture of traffic and transportation vehicles, compared to materials with a high specific strength. Materials with a low specific strength, while also having a high structural strength, are more suitable for the manufacturing of static structures, such as civil structures or buildings like houses. In structural design, form-resistant structure is also a very important concept. The form-resistant structure uses the design concept of higher sectional moment and moment of inertia, which under the circumstance of lower material usage can achieve better mechanical and structural characteristics, reduce the use of materials, and improve the strength of the structure. For example, in many structures, we will use special rectangular or eye-shaped cross-section materials, which can achieve better characteristics when bearing structural forces in a certain direction or by bending the steel plates into many irregular shapes, which can make the whole structure stronger when combined together, which is also one of the reasons why the monofoc frame structure is strong and durable. Next, we will provide several design concepts for strengthening the structure of the car body and provide you with a reference for the structure design of your compressed air racing car project. The next topic is the design and manufacturing methods for reinforcing the vehicle's body structure. First of all, what we see here is the cage structure reinforcement method. It adds an outer frame welded into the shape of a cage onto the original chassis design to strengthen it. With this method, a more sturdy car body structure can be designed and manufactured. The second method can be often seen in many car body structures. For parts of the structure that endure large forces, we design ribs and stubs, which can solve the initial problem of force concentration by dispersing the structural force at the location of the ribs so the overall strength can be improved. For example, on the bottom right is the chassis design of our compressed air racing car. We roll-pressed 2 ribs in the middle of the chassis, which can reinforce the original strength of the metal sheet to make the structure more sturdy and durable. The third method of structural design reinforcement is the use of sheet plates and join them together like jigsaw puzzles to make the whole structure more sturdy. The fourth method of structural reinforcement design of the car body is the use of arched, tapered, or variable shapes, which can be often seen in the design of containers, which uses binding techniques to increase the container's strength. For racing car design, for example, the use of arch shapes on the front of the F1 racing car can reinforce the passenger area's overall structural strength. Or the use of this kind of hemming to improve the structural strength of the body to keep the racing driver safe in the passenger area. For example, as shown in the lower right figure, two circular folded edges are rolled at the middle of the steel sheets of the chassis of our compressed air racing car. These arc-shaped edges can make the overall structure of the vehicle body more sturdy. Therefore, we can punch some holes in the middle. Not only it improves its strength, but also reduces the weight. The fifth method to strengthen the car body structure is to use composite materials. Composite materials are made by combining two materials with different physical properties. They can complement each other and bring out the better physical properties of the materials, such as the commonly used composite glass fiber board or carbon fiber board. Besides the high-strength physical properties, they have more toughness and can withstand greater external impact and achieve the goal of structural strengthening. Two other structural design forms are provided here, which can improve the overall structural strength. For example, the body structure is clamped together piece by piece in an arc-shaped manner. This kind of structure can withstand greater external force and improve the overall structural strength. Another mode of structural design strengthening is to use the method of glass fiber molding, which is similar to the concept of monocoque structure. The components are integrated into a one-piece structure that share the bearing force with each other, so the overall structural strength is enhanced. Making the chassis. Contour width of 10 millimeters. Wheel diameter of 40 millimeters. Use a divider to measure the dimensions we need. The technique of drawing a line on the steel sheet, we can use the divider guided by the edge of the galvanized steel sheet. We draw the width that needs to be trimmed off for the wheels. The distance of the lines drawn are equal every time. Next, we measure the diameter needed for the wheels on either side. Here, we adjust the divider to 40 millimeters long. The divider used here has a quick adjustment mechanism design. Now we rotate the steel sheet 90 degrees and draw the 40 millimeter space needed for the width of the wheels. Because the steel sheet has a reflective surface, we use a marker to mark the point of intersection. After that, we also use the marker to draw the lines that need to be cut more clearly, so that we can see with ease the position of the lines when cutting. Next, we measure the location of the holes needed for the axles. Here we adjust the divider to 15 millimeters. In the same manner, we use the divider guided by the edge of the steel sheet to draw the 15 millimeter distance required for the drilling of the holes. Next, We measure the 20mm distance needed for the front and rear axles and mark the position of the rear axle and the position of the front axle on the steel sheet. We also use a marker to mark the location of the drilling holes. Finally, we draw the 20mm distance needed for the cutting line for the hemming on the steel sheet. In the same manner, we use a marker to draw the cutting line clearly. Before starting the cutting, we check that all the steel sheet's expanded view are correct. Then, we use aviation scissors to cut out the space required for the tires. Use a rubber hammer to flatten the warped parts. We also use a hammer and a center punch to mark the position of the holes. This positioning method can guide the drill for a more accurate drilling. We use a step drill bit to drill 4mm holes. To make the drilling operation safer, we use a wooden cushion block with a guard to prevent the material from being spun around by the drill, which can be dangerous. After drilling, the backside of the plate often has the issue of protruding burrs. We use a file to remove the burr so that it would not cause dangers upon use. Let's just touch it with our fingers and check that it doesn't cut. Next, we will demonstrate 2 ways to hem the edge. Method 1. Use a rubber hammer to hit the plate on the steel anvil at its edges. Hammer the edge flat first, then slowly in a tilted position, and finally turn it to 90 degrees and hit it from the side. Hammering from different angles often has dead angles, so we often need to change to different hitting points. Everyone should be proficient in this way of hemming the edges. At this angle, we turn the steel plate 90 degrees, and the side of the steel anvil is the front of the steel plate. Slowly tilting the hammering, beat until you hit the front of the steel anvil at 90 degrees. Finally, we check that every hem is 90 degrees. This is the hamming method using a steel anvil for hammering. Finally, the teacher wants to remind you all that we must use a PVC hammer or wooden hammer on the steel anvil. If we use an iron hammer, it will cause the stretching of the material and cause a destructive damage to our material. In the second method of hamming, we use hamming pliers to clamp our material, aligning to our hamming line mark, and bend it by 90 degrees, which can also achieve the hamming effect of the metal sheet. After bending the chassis of the vehicle into shape, many corners may have sharp burrs, which need to be removed with a file to avoid injury. Finally, we also use our finger to touch and see if there's any place that still cuts and needs more filing. Hello everyone. In this unit, we will arrange a practical activity for the production of vehicle axle system and chassis. This chassis will be used for future testing on our compressed air racing car. The design of the chassis system has three characteristics. 1. A ladder frame structural design that can undergo repeated high-intensity testing. 2. No additional bearing system is needed, which can reduce the material cost of our practical activity. 3. A flexible body design with a chassis structure that can combine with different car body designs. We plan on spending 90 to 120 minutes on the practical event. Once the chassis is finished, we can perform the rolling resistance experiments of the vehicle as well as the related activities on the development of the vehicle's body styling design. For this topic, we will use the net drawings of engineering design sketches to let students learn how to use plate-shaped materials, such as iron plate, aluminum plate, plastic or paper sheets, etc., to make the planar unfolded drawing of three-dimensional figures. Such practical design drawing techniques are also very important operational skills. For this practical activity, measurement and sheet metal forming tools will be used. These tools are very easy to obtain. Please prepare them before the start of the practical activity to facilitate the subsequent activities and production projects. Other tools related to the sheet metal forming are also briefly introduced here. For the practical activity, we can use regular hand tools, or if the school has this kind of manufacturing equipment to aid even more in the process of this practical activity. The photo on the left is an anvil used for traditional sheet metal forming. If the school does not have this kind of equipment, steel bars or iron plates can also be fixed on the edge of the desk and be used for sheet metal forming. The photo on the right is a multifunctional sheet metal forming machine, which can cut steel plates, hem steel plates, and roll forming. If the school has this kind of equipment, the production of the chassis can be easier and more convenient. Most of the work can also be done using hand tools. We do not necessarily need these machines. In addition to the hand tools and equipment needed for sheet metal forming, we can use a hole saw to quickly turn our material into circles. For subsequent experimental testing, in the following video, the teacher will actually make this standard chassis that you can see in this picture. Here is a demonstration of how to use a hole saw to manufacture tires for testing. For the material of the tire, we will use 20mm and 15mm thick birch plywood. Cut into rectangles, which is convenient for the safety of the students. Replace it with 3mm diameter drill bit used for the fixture of the tire axle. There is a trick to using the hole saw. We can expose the edge of the blade to the outer edge of the material so that the swarf can be removed through the crevice. The cutting speed can be faster. When we feel that the drill has more resistance, we should pull the drill back up to allow the swarf to be removed. This way of cutting is correct and safe. Remove the hole saw. Use a round iron rod to push out the wheel stuck inside. Next, we use the router to trim the burrs on both sides of the tire into a circular tire with a 3mm fillet. Hold the material with the index finger of the left hand and rotate the material with the right hand in the opposite spinning direction of the tool to cut out steadily the fillet that we need. Finally, we finished making the wheels used for testing. Here is a demonstration of the production method of the guide sheet used in the test of the compressed air racing car. Method 1. Use a round anvil and a spherical punch to make the guide sheet. Here we use a 1mm thick galvanized steel plate. We measure 40mm material length and cut it out. File the cross-section of the plate to prevent sharp edges on the surface of the material. We use a protractor to align the material 90 degrees to the axis of the anvil. Next, place the sphere punch in the middle of the groove and hit it with a PVC hammer to make the material into a circular arc. Then we use wire cutters to adjust the curvature of our arc and make both sides symmetrical. Then use the sphere punch to shape it to make the shape more consistent and symmetrical. Use a marker and measure the left and right sides and mark the symmetric point of hemming. Use wire cutters to bend both sides of the steel plate by 90 degrees so that it can be fixed onto the chassis later. Finally, we use a PVC hammer to adjust the guide plate into its final shape. Let's first install the axles of the chassis and see where the guide plate should be fixed to avoid its obstruction with the axles. Mark the positions of the drill holes with a marker. Here we use a divider to mark the location where we want to drill the hole on the chassis. The left and right sides should have the same depth and symmetric. Use the center punch to position the drilling location. Adjust the height of the drilling machine and use a 2.5mm drill head to drill the rivet holes. The size of the guide plate is relatively smaller, so it is safer for us to use wire cutters to hold it before drilling the holes. We use a round file to smoothen the edges of the guide plate so that it can move on the cable with ease during future testing. Finally, we insert the rivets and the chassis plate. After the two plates are buckled together, use the rivet gun to pull out the iron rod in the middle. The final result is that the rivet will clamp the two materials together. This is the first method, the method of using rivets to fix the guide plate onto the chassis. Method 2. Use a resistance spot welding machine and use a washer as conductor. Wear gloves to protect our hands when operating. Put the washer on the chassis plate. Step on the switch of the spot welding machine to let the current pass, and the two materials will be welded together. This is the method of using the resistance spot welding machine to weld the washer onto chassis to make a guide plate. Finally, use the wire cutters to bend the washer 90 degrees, and then it can be used as a guide plate.